Alright, so nuclear decay provides a pretty reliable way of calculating the ages of rocks and minerals that contain particular unstable isotopes that will decay. This procedure is called radiometric dating. So when I say that it is reliable, I know this is the case because the rates of decay of certain isotopes have been measured and do not vary under different physical conditions that exist on Earth's outer layers. Therefore, the rates of decay are fixed for each unstable isotope that forms inside a mineral crystal in which it is found. And the products of this decay can be found within that crystal as well. And we'll go through that process in a bit. So for example, some minerals are able to incorporate uranium atoms in their crystal lattices during crystallization. When the mineral crystallizes, it has no lead, which is the daughter product of any previous decay. So it is at crystallization that the radiometric clock will start. And as the uranium starts to decay, there is increasing amounts of the lead within the crystal, which doesn't escape for the most part. The same thing happens with potassium feldspars, for example. And this doesn't happen with uranium, but it happens with another radioactive isotope, which is potassium-40. Potassium-40 will decay by electron capture to argon-40. And with time, argon-40, which is the daughter isotope, will increase and increase, while the potassium-40 will decrease and decrease within that potassium feldspar sample. So the time that is required for half of the nuclei in the sample of a given unstable or parent isotope to decay is called the half-life of that isotope. Okay, so the amount of time required for half of them to decay is the half-life of that isotope. The figure that you're seeing there on the slide shows this process quite well. So every half-life that passes, which is, again, half-life is going to be here on the x-axis, half of the parent material will decay to the daughter material every time. So again, if you start with 100 parent material, blue is the parent material, at one half-life, you have 50 of the parent material and you have 50 of the daughter material. At two half-lives, because you used to have 50 of the parent material, now you will only have 25 of the parent material. And you will have 75 of the daughters because you added the first product from the first half-life and then the product of the second half-life, which was 25. So you get the idea of how that goes. Every half-life, you get increasing amounts of daughter isotopes, and then you have the decreasing amount of the parent material within the sample. So, for example, if in a potassium feldspar sample that we had, we find that there are 5 atoms of potassium-40 and 15 atoms of argon-40, then we know that the potassium-40 has gone through 2 different half-lives. The first one, cutting the 20 initial atoms of potassium-40 into 10 parent, 10 daughter, and then the second half-life cutting the 10 remaining parent isotopes of potassium-40 into 5 parent and 5 daughter, which overall results in 5 atoms of potassium-40 and 15 atoms of argon-40. So, if the half-life for a given radioactive isotope's decay is known, if you know it, and you know the number of atoms of parent and of daughter material, then an age can be found for that mineral's crystallization time. The table that you see on the slide up here shows the half-lives or the half-life values of 5 different radioactive isotopes that we usually use in geology. We commonly use in geology. The first one right here is uranium-238, which I already gave you an example of. And here the uranium-238 is going to decay to the daughter isotope lead-206. You also have uranium-235, which decays to lead-207 at a much faster rate, as you're seeing here. We have thorium-232, which decays to lead-208 at a much longer rate. We have rubidium-87 to strontium-87 at a pretty large rate. And then the one I mentioned just now, we have potassium-40 decaying to argon-40 at a much smaller rate, or an in-between rate, I guess. So, if we use the same example that I gave before, because potassium-40 has or had undergone 2 half-lives, and each half-life represents 13 billion years, then the sample is about 2.6 billion years old. So it crystallized, or the mineral on which it is found, that potassium feldspar, crystallized 2.6 billion years ago. The table that you have here at the bottom also shows some other radioactive isotopes that are used for dating more recent events. Those isotopes tend to help us with different archaeological findings, for example, but these specific ones help us date groundwater travel times, more specifically. So the half-lives of these isotopes are much shorter than the ones in the table up here. These half-lives tend to be between 1 million years and 10 years. So they let us, again, date more recent events. I should also clarify that there is no need for the whole parent material to undergo one full half-life before we can detect some daughter material. The principle here is really to measure the parent to daughter material ratio. And use the half-life to find the age. I also want to mention here when we're discussing this numerical dating that although the process is incredibly useful, the techniques used for measuring the number of parent-to-daughter isotopes are very, very precise. And in some cases, like the one of uranium-238 decaying to lead-206, as it is shown in the image right here, there are many steps from the decay of parent material to the daughter material. So it's hard to keep track of these steps, and the number of of parent to daughter material and intermediate steps may introduce some error into the measurement. There's also potential sources of error when you're doing this radiometric dating by human or tool error, obviously, but there's also error introduced by the earthly processes that have shaped and brought the mineral where those atoms are used or are at. So, for example, there could be, for example, a leak of parent or daughter isotopes into the surrounding rocks since the mineral crystallized. It is relatively possible and common, for example, for this to happen to the daughter isotope daughter 40, or argon 40, excuse me. So argon is a gas, and it may leak very easily from the mineral's crystal lattice once it has decayed into argon. Another example of this introduction of error may happen when you have addition of more parent or more daughter material by the deionization of the flowing water that may be in contact with the mineral. So some of the ions that the water carries may be the same as the ions of the parent or daughter isotopes. So by the water carrying those ions, and those ions basically precipitating or reacting with the rest of the mineral's ions, are going to be adding more of that isotope to the count, to that measurement that we're doing. So overall, to avoid error, typically many samples, or the samples that are collected are subject to two different types of numerical dating, and so these are cross-checked. So if the cross-checks agree, then the likelihood that the sample is calculated right increases, but if the cross-checks don't agree in terms of age, it is less likely that that is the case. Then it's more likely that some sort of error, either human or based on the leakage or addition of parent or daughter material, happened. Zircon crystals are very common to contain uranium atoms, but not lead atoms during their crystallization. So, finding a rock that contains zircon crystals which formed at crystallization within the magma at depth is typically a good dating tool used by many geologists that I know. Many times, the zircon crystals are not in the igneous rock from which they crystallized, but they appear incorporated within sedimentary rocks. However, we need to remember that if that is the case, it does not mean that the sedimentary rock age is the age of the zircon crystal, but that it must be younger than the zircon crystal's age, because the zircon's radiometric clock started as soon as it crystallized within the melt of the magma, and the sedimentary rock lithified once the zircon crystal underwent surface processes some period of time after it crystallized. So through radiometric dating, we found many important dates, such as again the age of the Earth to be 4.6 billion years, but we also found different ages of the oldest rocks. The oldest rocks that we have found thus far are in northern Quebec and date of 4.28 billion years. And these rocks are probably from some sort of proto crust. But old rocks and old minerals have been dated in every single continent, ranging from somewhere between 3.4 billion years old in South Africa, or sorry, in Africa overall, in South America, and in Greenland, going all the way to 4.3 billion years old, some places in Australia and in North America. So you might know about this, but to date more recent events, a carbon-14 is typically used. So carbon, as we saw in earlier slides, has three main isotopes: carbon-12, carbon-13, which are both stable, and then carbon-14, which is unstable or radioactive. The half-life of carbon-14 decaying into nitrogen-14 by electron capture is only of 5,700 years, more or less, which allows us to date historic past events, as well as more recent geologic past. However, it is no longer useful for any material that is older than about 100,000 years, as the remain of the parent material is basically negligible once it gets to be this age. So carbon-14 is continuously produced in the atmosphere as the result of cosmic ray bombardment. And this carbon isotope is quickly incorporated to form atmospheric CO2 and can either remain in the atmosphere or it can combine with water vapor and fall as carbonic rain. Either way, you and other living matter end up using the CO2 for either photosynthesis, or for consumption in one way or another. And so you and those other living organisms are partly made up from this carbon-14 isotope, as well as carbon-12 and carbon-13, of course. And so all of these are usually in constant proportion with one another. So let's say if I have 100 isotopes of carbon-12 and I have 13 of carbon-13 and I have 2 of carbon-14, I will continue to have them in that proportion with time, because that's how available they are in the atmosphere and in the living matter which I consume.